to a lower energy, but in the process, it does a job. And the job that it does is it eventually docks onto carbon atoms, hydrogen atoms, and forms sugars, carbohydrates, all of the organic material that is, in trees and flesh and everything else. So all of that organic matter that we use, that we eat as food, that we burn in our cars as fuel, all of that is essentially an energy form that was created for us by the plants using the energy from the sun. Right? So this energetic process is a central process in our world. And one of the things that we do as human beings is we look out at biology and we try to figure out ways to mimic it. Right? And understanding this system has driven us towards photovoltaics, right? So the solar panels that are on our roofs are basically humans trying to copy or mimic this process. We've done it with solid state devices, non-organic devices, in the past, but one of the things that's being done these days that you may have heard of, that slide was just showing the Calvin cycle, we'll get back to that, is that we've, through understanding how the photosystems do this energy conversion, we've begun to design organic-based solar cells that essentially do the same thing. They take an organic molecule that has a conjugated pi system that's able to absorb a photon and promote an electron to an excited state. We take these organic molecules and stick them in the appropriate environment and create a cyclic current loop and essentially derive solar power from that. Have you heard of dye-sensitized solar cells? Is anyone at this? Yeah.
We're doing research downstairs on.
You're doing research downstairs on? I had a chance this summer to build a few. They're pretty fun. They offer the possibility of having a cheaper version of solar power, lowering the barrier of entry. Not just anyone can build a solid-state solar cell, but anyone can build one of these organic-based solar cells. So this is an illustration of why it's important to study chemistry. This is an illustration of why it's important to study biological systems, because we can take the methods, the mechanisms that are being used by biological systems, and if we understand their energetics, we can mimic them for our own benefit. So we go from photosynthesis to our own organic-based solar technologies. The slide that I skipped, sorry, was just the Calvin cycle, and the Calvin cycle shows how energy, let's see, we go back here, these photosystems take these excited state electrons, they drop them off onto these electron carriers, NADPH and NADP. They also make a little bit of ATP in the process. Those molecules themselves get fed into the Calvin cycle, and once they're in the Calvin cycle, the high energy state electrons that are residing on those molecules get dropped off onto carbon dioxide, and you end up making strings of carbohydrates, sugars, based on this process, yielding glucose and other things. So I was just showing you more specifically how the sun achieves that end. Another thing that we borrowed from nature, or maybe we didn't borrow it, but nature did it first and we did it later, is combustion. So all of these carbohydrates that are made by the plants, we ingest them, and our biological organism takes the high energy electrons that are stored in those carbon-carbon and carbon-hydrogen bonds and breaks them apart to form ATP and NADPH and things like that, so that we can run our metabolic system. This is universal across biology. All of these biological mechanisms do this. When we take those high energy electrons, those electrons in the carbon-hydrogen, carbon-carbon bonds, and break them apart, we end up forming carbon dioxide and water, right? we take carbohydrate, take the energy stored in carbohydrate, and we allow those high energy electrons to move from the carbohydrate to oxygen molecules. And that's kind of the definition of a combustion reaction, is to take a carbohydrate and to turn it into carbon dioxide and water. And essentially what that is it takes advantage of the fact that an electron that moves from a carbohydrate to an oxygen molecule is moving down an electric potential. I'm going to try to chalk talk this one for a second. So we've got methane, each of these methanes is or each of these carbon hydrogen bonds is a shared pair of electrons, right? I'm not drawing a double bond there, just showing there's two electrons. I sometimes use notation that you haven't seen in chemistry before. So we've got shared pairs of electrons there. Those electrons are bound to carbon and hydrogen, right? Carbon and hydrogen are not the most electronegative atoms in the world. They hold their electrons relatively loosely. Oxygen, in the form of O2, is a situation where oxygen, which wants to fill its valence, wants one more electron to fill its valence, has been forced to pair with another oxygen because there's no other candidate available to share an electron. This is not the most comfortable state for oxygen, right? Oxygen's in a tug of war for electrons with an atom that is equally as strong as it is at pulling on those electrons. The oxygen atom itself would like to, if it had the opportunity, to pull that last valence electron closer to itself. But here, it can't. Right? So it's sharing with another oxygen. In this molecule, these two electrons are bound to carbon and hydrogen. They're pulled a little bit more closely to the carbon than the hydrogen. But essentially they're at a higher potential, a higher energy. So we can show the electrons up here in a carbon-hydrogen bond. They're at a higher potential energy than they would be if they simply came down here and formed a carbon-oxygen bond or an oxygen hydrogen bond. Right? CO2 here. The reason for that is kind of the following. This is over here. Grab some more space. Have you seen this equation? The force is Q1 times Q2 over 4 pi epsilon naught r squared. Right. That's the r squared force law. It describes the force of traction between two charged particles. And we know that as two charged species approach each other, that energy is released, right? Energy that was stored in an electric field is released. If you take a positive and a negative charge, and they're sitting on top of each other, and you try to force them apart, they resist because they're attracted. And so you have to push with a force to separate those two charges. There's energy put in to separate them, and similarly, if you allow these two charges to move together, energy is released. And it's kind of an electric potential energy that's released when those two charges are allowed to gain a closer approach. So let me ask you this question. If I have an electron and I have some positively charged nucleus, and I allow, let's say I have two positively charged, one that has more positive charge than one that has less. If I allow this electron to approach that nucleus and it moves down, there will be this force that's proportional to the charge of the electron, the charge of the nucleus divided by 4 pi epsilon naught r squared. There'll be that force that acts over a distance as that electron moves closer to this atom. And when that happens, it releases energy. If I allow that electron to approach this atom, if I give it the choice to approach this atom or approach this atom, which situation results in the release of more energy?
Would be that one with more?
Yeah, this guy. This guy exhibits, it pulls on this electron with a greater force than this one does. And so an electron that approaches this atom, this nucleus, goes to kind of it ends up at the end at a higher energy state than the electron that approaches this one. More energy is released, therefore the energy state of the electron bound to this atom is lower than the energy state of the electron bound to this atom, right? And that's all that's really going on with these combustion reactions. We've got oxygen atoms, which are that more electron-hungry atom, right? There's more charge in that oxygen nucleus. There's also kind of a greater incentive for the electron to move to that oxygen because it fills its octet. I believe that that electron also has a closer approach. So when we're calculating that, that integral of the energy, the R distance, the distance that the electron moves in, it moves into a closer distance here on the oxygen. So essentially, more energy is released when an electron moves to an oxygen than when it moves to a carbon or a hydrogen. So if we take this species that has electrons bound to carbon and hydrogen, which are relatively higher in energy, and we break those electrons off of this species and we let them fall onto this species, there's an energy release that results because of the fact that that electron becomes more tightly bound when it's on oxygen than it was when it was on the carbohydrate, right? So this is the task that plants have handled for us. They've built all of this carbohydrate, all of these high energy chemical bonds, and then our biological systems have developed ways to throw some oxygen into the mixture and allow those electrons essentially to fall back down onto the oxygen atom and release that energy that's a result of the relative electric potentials of the electron in the two states. So our systems do this. We take glucose, that's our carbohydrate, got a bunch of high energy electrons, we break them apart. What the hell? And we let them fall back down onto oxygen. The carbon electrons end up bound to the oxygen, forming CO2. The electrons that were in the hydrogen end up bound to oxygen, forming H2O. So both of those electrons in the carbohydrate, the electrons that had belonged to carbon, the electrons that had been bound to oxygen, move in towards that oxygen atom and they release the energy. We form carbon dioxide and water, and the energy that's released, we harvest it in the form of ATP. Yeah? So biology did it first, and then we did it second. We said, hey, there's all this energy that gets released when carbohydrates and whatever carbon and hydrogen and electrons recombine with oxygen. So we're gonna build an entire fleet of SUVs based on that technology. So it's important to understand the chemistry and biology. It leads us to being able to mimic that and create devices of our own. Everything is energy. Everything is about creating different energetic scenarios that lead you to being able to do things more effectively and more efficiently. Nature does it all the time. Enzymes essentially take electrostatic forces. They have different amino acids that have positive charged sides and negative charged sides. They'll use those amino acids to hold reactant molecules in particular positions. Once those reactant molecules are held in a position, they can drive certain reactions. They might drive a reaction by sucking electron density away from a center that ultimately needs to be attacked by a nucleophile, making it more nucleophilic, so they can speed the rate of the reaction that way. They can make sure to hold reactants in a specific position that leads to one kind of stereochemical product. You guys have taken organic chemistry, so you're familiar with stereochemistry, right? There's different reactions can give yield to this, isomers, but if you hold reacting molecules in a certain orientation, then you can minimize the chances of forming the wrong isomer. So biology uses these energetic principles all the time. That's how we end up with our amino acids having the appropriate stereochemistry at every single center, at every single link, is because those guys are formed by enzymes. Data. DNA is just all data. So biology has figured out a way to use, again, it's just electrostatics. We've got our bases, which have the ability to do hydrogen bonding. There's energetic minimums that these bases achieve once they pair together. There's machines that are built to read the specific kind of electrical communication that happens on each of those bases, and it's so reliable that we can use it to store huge amounts of information. Right? It's all just energy. Oxygen binding. We've got this protein hemoglobin, and its job is to go into an area of high oxygen concentration and pick up oxygen. And then it moves into an area of low oxygen concentration, and once it's in that area of low concentration, it dumps it off. This is a very sensitive reaction. You can imagine that if you were to bind an oxygen molecule in an area of high concentration, but you bound it too tightly, and then you move it into an area of low oxygen concentration, it would be difficult to get that oxygen molecule to pop off. So the energetics of physically holding that oxygen in your protein have to be absolutely perfect, such that you can pick it up and still drop it off. If you have to hold it tightly enough to pick it up. If you don't, you can never pick it up. If you hold it too tightly, once it becomes time to drop it off, you can't drop it off. So these molecular machines are constantly playing with energetic states and finding just the right amount of force requisite to do their job. This is another one that biology uses. Biology takes advantage of the polarity of amino acids and water molecules to bring a polar molecule of water across a non-polar surface or non-polar volume. Right? Our cells are made of fats, lipids, and those van der Waals forces hold the fats together in a hydrophobic environment. And those lipids stack on top of each other, they make our cell walls, but the entire cell wall is hydrophobic. Hydrophobic means that water can't pass across it. We need water in our cells. And so biology has made these proteins. These proteins have wrapped themselves in such a way that they're outside is all hydrophobic and has favorable interactions with the hydrophobic lipid bilayer. And so the protein itself is able to sit across that cell wall in that hydrophobic environment. And then the inside is made of polar amino acids that are hydrophilic that have an attraction for water. And so that creates an energetic state where it's favorable for something that is polar to end up crossing a non-polar boundary through a little port that also happens to be polar based on the way that protein folded. This whole system is finding an energetic mechanism to bring that polar molecule energetically, to create an energetically favorable situation for that polar molecule to cross that boundary. There's another kind of energy that we'll talk about, energy stored in concentration gradients and electrical potentials. There's concentration gradients, there's electrical gradients, but our cells, our nerve cells, take advantage of those. We've got an electrical potential and a concentration potential developed out of favorably pushing sodium or potassium to one side of the cell or the other. We end up with more positive charge on one side than negative charge, and so there becomes an energetic incentive for charge to pass from one side to the other. But there's also a concentration gradient, and so we've got more potassium on one side and more sodium on the other, and so there'll be an incentive for the molecules to move from one side to the other based on just their charge. And so there ends up being a push-pull relationship between your electrical gradient and your concentration gradient. It creates this energetic system that allows a signal to fire all the way down your nerve cell from one side to the other. Right? It's all just using energy. Energy stored in different forms. Concentration gradients, electrical gradients, whatever it is. So energy's out there, it's everywhere. It's important to understand it so you can understand how systems function. There's the other one, the last one I'll throw at you. Another way that biology uses thermodynamics. This is an important one. It's important for our class because we'll be going into some of the thermodynamics of these state changes. But evaporative cooling. When water goes from the liquid state to the gas state, it absorbs energy. The reason for this is that water's a polar molecule. Two water molecules are attracted to each other. They're stuck together by essentially their electric forces, right? The negative side of one water molecule and the positive side of another molecule are stuck together and they're attracting each other. And if you want to separate them, you have to put energy in. And so energy is absorbed when water goes from the liquid state to the gas state. There's an energetic drive for anything to go from, to move into areas of lower concentration. And so if you have a hot, humid day where there's not a lot of water vapor in the air, then water on your skin will kind of naturally be inclined to move off of your skin into the dry air. When it does that, it sucks in thermal energy from your skin to make that transition from the liquid state to the gas state. And so this naturally cools your skin. The fact that this water is pulling the energy that it needs to transition from liquid to gas state away from your body has a cooling effect on your body. Nature figured this out. This is why we sweat. This is why dogs pant. And sometime after nature figured it out, we figured it out and we made swamp coolers. You ever seen these swamp coolers? I don't know if they have, do they have swamp coolers in San Francisco? No. See, I grew up in Red Bluff, California, where it's 120 degrees in the summertime and it's always really dry. And the swamp cooler was one of my greatest friends. So the swamp cooler means a lot to me. What the swamp cooler does is it takes essentially a volume of water and blows it out into dry, hot air. And when that happens, the water making that transition from the liquid state to the gas state sucks thermal energy out of its environment and cools the air. And so the swamp cooler is the human beings, it's the engineering application of the biological system, right? It's all energetics. It's all energy transformations, thermodynamics, etc. I thought I was moving too fast. Now I think I'm moving too slow. I'll try to slow it down a bit. So, a roadmap for what we're about to do. Got a few things that we need to start thinking about. Ultimately, we want to leave this course having a really good handle on what makes a reaction spontaneous and what we need to do in order to create situations that make a reaction spontaneous. We want to understand the energetics behind equilibrium, what is necessary for two states or for two systems to come into equilibrium. In order to do this, we're going to have to develop some tools. And one of the first tools that we're going to develop, or the first things that we're going to try to understand, is this concept of the internal energy, U. And so the internal energy, we'll discuss it more as the course goes on, but you can think of it in general as just the total amount of energy that a system of matter contains. And we'll look at the different ways that matter can house energy. There's energy associated with something that has mass. There's energy associated with the motion of the matter. So if a molecule or whatever is moving, then it's got kinetic energy associated with that movement. There's an energy associated with any kind of an electrical potential. So we use the R squared force law over here, and we said that it takes energy to separate a positive charge from a negative charge. So anytime that you have a system where there's something that can be thought of as a positive charge and a negative charge that have been pulled apart, that system contains a potential energy associated with those relative positions of the charges. So the internal energy of a system, U, is a function of the motion of the molecules, the motions of the mass, because we have kinetic energy, and any electrical potential that exists, any separation of charge that exists in that system. We're going to introduce the internal energy, and then we're going to start kind of conceptualizing how energy can move from one system to another. And we're going to use two thoughts, or two kinds of mechanisms. We're going to learn to think of energy transfer as happening in the form of heat and the form of work. Now, the heat we're going to think of in terms of kinetic energy being transferred from one system to another. And often, or many times, this is transferred in the form of collisions. So if two particles collide and one of them delivers a good chunk of its kinetic energy to the other particle, then there's been an energy transfer that has resulted in the particle that had the energy delivered to it moving faster than it was before. So it's gained a kinetic energy, and we consider that to be a heat transfer, transferred through inelastic collisions. Work takes different forms, and it's kind of tricky when we get into some of these problems because there's work that immediately gets turned to heat, and so it's difficult to see the boundary between work and heat. But what we're going to do is we're going to think of work as energy that's transferred when one system acts to change another system's potential energy. So if we have, as we've seen this one a million times, we have a ball sitting at the bottom of the hill, and it's got some mass, and we act on it with a force to push it up to the top of the hill, then its potential has changed, right? The same way we've got those two charges separated, and we push on them with a force to separate them, we change their potential. That action is what we think of as work. So You guys know the equation from physics, work equals force times distance, F dot D. It's the integral, work is the integral of force with the distance. Work, the work that we're going to be dealing with is just that. It's using a force, acting on a system with a force that acts to change that system's potential energy, right? So we're going to think of internal energy. We're going to learn how internal energy can be exchanged